Nice. Hello, everyone. Very nice to be here. Today, I'm going to speak about on-chain privacy and client-side data management. Let's start. From ancient times, people were concerned about on-chain privacy. On this picture, you can see people are trying to hunt privacy. It's not easy. It's not easy because it's not like when we ask, like, what is on-chain privacy? To hunt, to catch something, we need to understand what we are catching. And on-chain privacy is a bit vague definition. So let's think, which creature are we going to hunt? Not any privacy. At least we want privacy on Ethereum. Why? Because Ethereum is, first of all, because we love Ethereum, but not only this, because it is a robust layer, and it makes a lot of sense to build our privacy layer on top of a robust layer. So we want our privacy layer to be on top of Ethereum, meaning we want our privacy layer to be on top of fully transparent layer. That's already quite tricky. But OK, if we stick to this construction, will still any privacy work for us? Like, let's think. We have some monolithic, isolated private layer, and some stuff is happening inside. And are we happy with that? Not really. Because what we want our privacy layer to communicate with the rest of Ethereum world. We want our privacy layer to communicate with Ethereum layer, with other layers, with other applications, because we don't want to be a lonely guy sitting in the corner alone. We want to be a cool guy integrated in the ecosystem. But even that is not enough. If we want to communicate with other creatures in the Ethereum world, for example, we want to communicate with Uniswap protocol, we need to be able to make some things public and some things private. Because, for example, for Uniswap, it should be able to update the state of liquidity pools, meaning that we can have the case when we have private users' identity, but we still have to make public the amount of token and what was swapped. Otherwise, we are the lonely guy sitting in the corner alone. So this is our creature, and we are here to catch it, even though it's not easy. How could it look like? I don't know, but maybe like that. Or like that. Or like that. Something not very simple, pretty fancy, pretty cool, a bit tricky. So how to hunt the privacy creature? I will give you the full list, and then we go one by one and take a look at each of them. So we discussed already, we want to be on Ethereum, because we love Ethereum, and because Ethereum is a robust layer. We also want to have public and private state, because we want to communicate with the rest of Ethereum world. And we also want to have public and private functions in smart contracts, so that we can make choice what is public, what is private. And we want to utilize client-side proof generation for it. And we want this proof to be zero knowledge. This is extremely important. So we start with this state. Public and private state. For public state, it's pretty straightforward. Public state means available for everybody. It's like on Ethereum. It utilizes account-based model. And what it means is that this is the database with some keys and values. So in this example, keys are accounts, Alice, Bob, Charlie. values are their balances. When there is a transaction, the balances are updated. So Alice sends Bob 10, Alice's balance is updated, and Bob's balance is updated. That's it. Can we use account-based model for privacy? Let's think. If we just encrypt everything and now perform transactions on like that. Not really. Because if we execute a transaction on encrypted entries, people still can see which entries were modified. And by retrospectively analyzing accounts activity, a lot of information can be retrieved. And it means we already don't have any privacy. That's it. So for privacy reason, our friend is UTXO model. In UTXO model, account states cannot be modified. Instead, the model operates in the append-only manner, meaning that we can just add, only add, nothing else. And when we want to update an account state with UTXO model, we need to destroy some existing nodes and create some new nodes. Who are nodes? Just entries in the table we've seen several slides ago. Table, this is node. That's it. So let's see the same example, but now with the UTXO model. Alice sends Bob 10. What we do? We cross out Alice's previous balance. We create a node with new Alice's balance. And we create a node for Bob with his 10 balance that reflects the transaction. And now we can encrypt all the entries, make our updates without causing any privacy leak. That's what we wanted, because in this thing, the first and the fourth belong to Alice, but we have no idea from this. But now it's a bit tricky, because I first said append-only mode, where you can only add, but then I said, OK, now you need to cross out. So let's learn a bit how append-only mode works. Modifying an entry in the UTXO model means destroying the existing entry and creating a new entry or entries reflecting the transaction. How can the node be destroyed in the append-only mode? With the help of nullifier. A nullifier is a commitment corresponding to a private entry that was destroyed. That might sound a bit cryptic. Throw it away, look at the picture. We have our UTXO model. And by the way, we have trees here. We had tables before, but this is just the way to organize. It's the same database. It doesn't change anything. It just look better. So we have our UTXO tree. In the UTXO tree, we have some entry. We want this entry to be destroyed. What we do? We create a nullifier in a separate nullifier tree that corresponds to this entry. If there is a nullifier for the entry, it was destroyed. If the entry does not have a nullifier, it is still valid, it still exists. That's it. The trick is that only the node owner is aware of the correspondence between nodes and nullifiers. So if it is node of Alice, it's only Alice who knows that the nullifier exists for this node. The rest of the world has no idea. So a bit different example. Alice has 100. So we have a node where Alice has 100. And she's sending Bob 10. So she destroys your 100 node, meaning that she creates a nullifier for this particular node. And she also creates a node for Bob with 10, and a node for herself reflecting her updated balance of 19. So you see, Alice had a node. She creates a nullifier in the separate nullifier tree, meaning that this node doesn't exist anymore. Instead of this, there is a new node with 90 for Alice and with 10 for Bob. Bob then can decrypt the node, get access to his 10, and he's happy. So I hope I convinced you that for public state, it makes sense to use account-based model. For private state, it makes sense to use UTXO model. And we got some intuition how they work, and what is more important, why we made this choice. So now we have smart contracts on Aztec that consist of public and private functions and also public and private inputs. And developers can choose what to make private and what to leave public. Why do we want it? Because we want private DEXs, or we want private lending, something that requires some external party to be aware of some piece of information. For example, if we are doing decentralized lending protocol, and we want anyone to be able to join as the liquidator should be aware, for example, of the collateral amount. So he knows, like, if there is any need to liquidate anything. So the smart contracts on Aztec are composed of private and public functions, and that gives us programmability. So now we have this fancy creature of smart contract we wanted to execute. How it is executed? First, all private functions are executed, then all public functions are executed. Whatever we want to stay private, it should be executed client-side on user's device. What it means client-side? It means either smartphone or laptop browser. The cluster of GPUs, even if I'm user and they are my personal GPUs, do not qualify as user's device. Me and my friend third-party prover do not qualify as user's device for client-side proving. So the proof of correct execution should be generated client-side on user's device. Yeah, this is our friend, client-side proof generation. And yeah, all private functions are executed client-side. A proof of correct execution is generated and supplied to the mempool. And the sequencer verifies the proof and executes public functions and produces a block. So these strawberries guy are client-side proofs. They jump into the mempool. In the mempool, they are verified by the sequencer, who then executes public functions, builds a block. All good. But not as simple. What is the transaction floating in the mempool? These strawberry guys, I mean, what is the anatomy of the transaction? And it looks like that. We have client-side zero-knowledge proof. And we also have effects from private execution. Emitted node hashes, encrypted nodes, nullifiers, as well as requests for executing public functions. And there are many of them floating in the mempool. And the last but not the least, client-side proof should be ZK, meaning zero knowledge. Zero knowledge proof, zero knowledge snark. No, a regular snark does not qualify. Even if it is your favorite, the best in the world snark, but it's not zero knowledge, it doesn't work. Why? Because it leaks privacy. What is the wide definition of zero knowledge? It says that when the proof is verified by the verifier can't retrieve any additional information except for that contained in the proof. And in our case, the verifier is the sequencer, and it is very important for us that the sequencer, while verifying client-side proof, cannot retrieve any information about what has happened client-side. So let's wrap it up. We wanted programmable, composable privacy on Ethereum. We got it. For composability, we have private and public states. For programmability, we have smart contracts consisting of private and public functions and inputs. Private functions are executed client-side, public functions are executed roll-up side, and client-side proof should be ZK. Why does it matter? I mean, why does it make sense to make such a huge job of constructing all these new things? Otherwise, why does privacy matter? Whenever we want to build serious stuff, we need privacy. I mean, like DeFi, privacy. Identity, privacy. Products for emerging markets when people and governments are not really friends, privacy. Products for B2B and enterprise, privacy. Products for governments, privacy. A product where everything is public for everyone in the world just doesn't fit the reality. Of course, there are some cases when we don't need privacy. For example, if we are playing around in fun mode, only experimenting with tech, maybe that's fine not to have privacy. Sometimes privacy can be harmful. For example, if we are building an aquarium, imagine we are building an aquarium. We want everyone to be able to see our fish. If we make it private, aquarium doesn't work. But if we're serious about building real products for real users as real companies, and the product is not an aquarium, we need privacy. That's pretty much it. Thank you so much for listening. If you ever have any questions about privacy, zero knowledge, Aztec, whatever you want to talk to me about, I'm very responsive on Telegram and Twitter. Please message me, ask questions, argue with me, whatever. Thank you so much, and if there are any questions.
Hey, so I have a question because from what I understand, the contracts on Aztec are kind of private as well, right? So if you're executing a transaction that has to interact with a specific contract, do you need to know the code base or the bytecode of that contract to be executed? And if you need to do that, how do those bytecodes kind of get distributed to the users that actually need to interact with those specific contracts? And is that leaking privacy in any way as well?
The bytecode privacy is up to the developer. So depending on what someone is building, they can go with the option of bytecode privacy. But I think it's a binary thing. You either make it private or you make it public. You can't make partially.